Bismillah ar-Rahman ar-Rahim. Last lecture, we were talking about, we actually finished the number systems by discussing the final topic, which is related to BCD encoding and stuff like that, ASCII characters and parity bits. There is one more important question related to BCDs. Okay, so the question is that we saw some examples of BCDs. Okay, maybe 5 or 6 examples of BCD codes. However, there are much more examples that are, or much more BCD codes that are possible. So the objective of this slide or this attempt is to count how many possible BCD codes are there to encode decimal digits. Okay, so this is a simple counting problem. Okay, and you can find the answer to this in any introductory counting course. Okay, so we start with any digit. Okay, first of all, we start with any digit, like digit 0, for example. It doesn't matter which digit you start from by symmetry. Okay, so digit 0, for digit 0, if you have a 4-bit code that you would like to assign digit 0 to, then how many possibilities are there? Digit 0 have 16 possibilities, because you can assign it any number from 0000 all the way to 1111. This is basically in decimal corresponding to 0 to 15, which is 16 possibilities. Okay, so if you have 16 possibilities for the digit 0, then and you pick one possibility out of them, then you are left with how many possibilities for digit 1? 15 possibilities for digit 1. Then you pick one for digit 1, okay, and then you're left with 14 possibilities for digit 2, and so on and so forth until you reach digit 9 of the decimal digits, in which you have only 7 possibilities. So the way to calculate the number of ways is to multiply these possibilities by each other. Okay, so the answer to our question, how many ways can we generate BCD codes for decimal digits, is basically 16 times 15 times 14 all the way to 7. Okay, and this equals to 16 factorial. Okay, but we don't have 6 factorial here, so we divide by 6 factorial, okay, to get rid of it. This is exactly how many possibilities, how many possible code assignments are there. Okay, which is way more than what we saw in the examples. Okay, any question about this? Okay, let's switch to Boolean algebra. So now we start with unit 2, or the second part, second chapter of the course, okay, which is basically Boolean algebra. Okay, let me just minimize this. Okay, and it's full screen. How do I make it full screen? Yeah, better now. Okay, so Boolean algebra, in the Boolean algebra unit, the objective is to study design of what we call digital circuits. Now, digital circuits use the binary system that we studied. Okay, so the signals that are input to the to any digital circuit, okay, can be either logic 0 corresponding to low voltage and physically, and or logic 1, which corresponds to high voltage when we talk about physical quantities. Okay, so physical value can be high or low voltage. Okay, and logical value of a signal can be either 1 or 0. Okay, now this is the general model of a digital circuit. So we have a digital circuit as a black box here that consumes n signals labeled as x sub 1, x sub 2, all the way to n, x sub n, and output, okay, the output of the digital circuit. So it consumes these input signals, okay, which are called also binary signals or Boolean signals, okay, and it consumes them and produce some outputs, Z1, Z2, up to Zm, so M outputs, okay. So X sub I is input number I of the circuit, and Z sub I is output number I of the circuit, okay. So in generally speaking, we have Z sub I is a function of all the inputs, okay. It might not necessarily be the case, but this is in general, okay. So all the outputs are some function of inputs, okay. We call this Zi binary function or Boolean function, okay, and it requires the Boolean function, okay, manipulation and evaluation requires what we call binary logic algebra, or in other words, Boolean algebra, which is the common way to refer to this algebra, okay, Boolean algebra after George Boole, okay, a person named George Boole who derived the Boolean algebra, okay. So Boolean function, this is the way to use the keyword Boolean. Boolean functions take Boolean variables and produce Boolean outputs, okay. To design a digital circuit, we must know how to derive Boolean functions, okay. And digital circuits are commonly referred to as what we call logic circuits, okay. Logic circuits. When we say logic circuits, we mean also digital circuits. So the plan for the rest of this unit is to do these 4 things, okay. We will define Boolean algebra, and then list the gates that we will use and the operations, okay, and then list some basic identities and the duality principle, and then do some Boolean algebraic manipulations. All right, so let's start by defining what we mean by the Boolean algebra. So this slide defines the Boolean algebra structure. Okay, so it is basically a mathematical or an algebraic structure. Boolean algebra is an algebraic structure with 3 things here. First of all, there is a set, and then 2 binary operations and 1 unary operation. Okay, the set contains 2 elements for Boolean algebra, 0 and 1. And the binary operators are the and the or, and the unary operator is the not or the complement. Okay, so the complement is denoted by a bar over a variable or a prime right after the variable. Okay, so if you have these 3 structures, these 3 things here, 2 operators, okay, 2 binary operators, and 1 set with 2 elements, and 1 unary operator that satisfy these properties here, then we call this Boolean algebra. Okay, this is by definition. Okay, by definition. So what are the properties that are satisfied? First of all, the easiest property is that there exist 2 elements in B that are not equal to each other, which is satisfied by default. Okay, we have in Boolean algebra, we have 0 and 1. So 0 does not equal 1, okay? And then for every x in B, okay, this is called for every, okay, for all x in B, there exists x complement, which is also in B. So x complement is defined as if x is 1, then x complement is 0, and if x is 0, then x complement is 1. So it is always, it always exists and always in B, okay? Also, we require closure under and or, okay? So closure, what do we mean by closure? We mean if x and y belong, this is given, belong to B, okay, then we have x ANDed with y also belongs to B. This is closure under and, okay? Closure under or means that x ORed with y belong to B as well, okay? This is the closure property. What about the identity element? Identity element, okay, is basically the 0 for the and, for the or, and it's the 1 for the and, okay? What does identity mean? Who can explain the identity for us? Anyone? Wake up, guys.
Does it mean that 0 represents plus?
No, it's the identity. So when I say the 0 is the identity in addition, okay, what does it mean? It means if you add 0,
it doesn't make a difference.
so if you add 0 to x, the answer is going to be x. So this is what I mean. So here, the 0 is the identity for the or, okay? This is or. It's not a plus. It's not addition, okay? It's or, okay? So this means that 0 ORed with x is equal to x, where x is in B, okay? Also, 1 is the identity for the and. So 1 ANDed with x is x, okay? This is what the identity mean. So so this is we finished from that. So commutativity means commutative under plus and under or and, okay, means that if x or y equals to y or x, this is commutativity for the or, and commutativity for the and is xy is equal to yx, okay? It doesn't matter. The order of the operation doesn't matter, okay? Now the distributive property, okay, we have the and distribute over the or as well as the or distribute over the and. So one of them you are familiar with, okay, but the other one is a little less familiar, okay? It's not familiar at all, okay? So if we have x, okay, ANDed with y or z, then this equals, this is the distributive law. It's called the distributive law in Boolean algebra. X, it is x ANDed with y or with x ANDed with z. Do you see that? This is a distributive law of, there is another version of the distributive law in Boolean algebra, which will make you wonder, okay? So basically it's this. So x ORed with y and z, and you can also distribute this, okay? So x ORed with y ANDed with x ORed with z. This is true by definition of Boolean algebra, okay? So if you have all these operations, so this is the least obvious case, okay? So this is very important. It's very important to understand the distributive law in its two forms, okay? This form as well as this form. It will help you a lot if you digest this form as well in doing algebraic manipulation later. Okay. All right. Moving on. So as I told you, the plus represents the OR operation, and the dot represents the AND operation or operator. Okay. And the over bar is the unary operator for the NOT operation. Okay. Here is an example. So we have F that is equal to A ANDed with B, okay, ORed with 1, okay. Here in this example, we have a, first of all, we have F that is the Boolean output or Boolean function, okay. And then we have A and B that are Boolean variables, input, they are input. And 1, we have 1 as a Boolean constant, okay, constant. And now, and also we have the AND and the OR, these are, we call operators, okay. And there is also what we call operator precedence in Boolean algebra, okay, in which the highest priority is given to what is inside the parenthesis, okay. This has the highest priority. And then the unary operator, which is the NOT, and then the AND operator, and then the OR operator has the least priority. Okay, so if you understand this, then you can tell me which operation is performed first in this function.
A and B.
The AND, excellent. The AND operation is done first, and then the OR is done second, okay? So first we do the A and B, and then take the result and OR it with 1, okay? However, this is going to be different from, okay, if the precedence change and we give the OR more precedence than the AND, the answer will be different, okay? So if we do the B ORed with 1 first, and then AND the result with A, we'll get a different result, okay, different expression, okay? The correct way of doing it is A ANDed with B and take the result and OR it with 1. Okay, this is the operator, the correct operator precedence. Okay. Any question? Let me move on if there are no questions.
Yes, Doctor.
Yeah, go ahead.
What if we did the distribution in this?
You can, of course. Yeah, you can.
What will be the priority for the operation?
Yeah, so how can you distribute? So you have to distribute the 1 over the A and B, right? So
yes.
So you take 1. So it doesn't matter whether the 1 is in the left or in the right. So because of commutativity, right? You can say, well, this is equal to 1 ORed with AB, right? Yeah, it's equal to that. And then use the distributive law, which is 1 ORed with A ANDed with 1 ORed with B, right? So if you have this, now, how do you do the precedence? You tell me.
I don't know. That's why I ask you.
Okay, so go by the rules. Yeah, so parentheses first. Okay, so we do the parentheses. If you have more than 1, then you go left to right. Okay, so this is going to be evaluated first, 1 or A, then this is second, 1 or B, and then the result of this is going to be ANDed with the result of this. By the way, I think we haven't covered that. Let's not do it right now, okay? But this is an excellent question. Thank you for asking. Okay, did you get it?
Yes.
Okay, great. Okay, so moving on. So now we discuss the logic gates. So remember that when we say logic circuits or digital circuits or logic gates or logic circuits, we mean that really that really means electrical circuits. Okay, it corresponds to some physical transistors as well as other wires and stuff like that, and voltages and stuff similar to that. Okay, and switches, hardware. That is hardware, in fact. Okay, so there is a way to represent Boolean functions algebraically as well as physically, okay, or symbolically using gates. Okay, so the AND gate, which is the AND, which corresponds to the AND operator, which is this one here. Okay, so if Z equals X ANDed with Y, sometimes we don't write the dot. You don't have to write it. Okay, just X Y. This is represented using a half circle. Okay, half circle which has two inputs, X and Y, and the output is Z. Okay, so this is a straight line. Don't mind the it should be a straight line. Okay, and then this is a half circle. Okay, so this is how you represent the AND gate. And the definition, so there must be some way for us to compute what is X ANDed with Y. Okay, X is a Boolean variable which takes two values, 0 or 1, and Y is another Boolean variable which takes two values, 0 and 1. So the combinations, the possible combinations of X and Y are what? 2 times 2 is 4. We can have 4 different combinations of X and Y. And for every combination, okay, we compute X and ANDed with Y. Okay, so here are the values. So if you have 2 bits, X and Y, okay, then you just count. Okay, you count 0, 0 in binary, 0, 0, then 0, 1, and then 1, 0, then 1, 0, and then 1, 1, right? This is the maximum number you can reach using 2 bits, which corresponds to a decimal 3. Another way of doing this is to start with the least significant bit and then go 0, 1, 0, 1. And then for the next bit, you go 0, 0, 1, 1. So you double the number of zeros and ones every time you go to the left. Okay. Now for the AND operation, it is defined to be 1, okay, if and only if X is 1 and Y is 1. Okay. Otherwise, it is 0. So it is 0 here and 0 here, 0 here, and 1 here. Why 1 here? Because X is 1 and Y is 1. And Y is 0 here because Y is 0 here. Okay. And Y is 0 here because X is 0. And Y 0 here because either you can say because Y is 0 or because X is 0. Okay. I mean, when you say or, it means that both of them is fine as well. Okay. So mathematically speaking, you can define it using this definition here. Okay. X ANDed with Y is 1 if and only if X is 1 and Y is 1. Otherwise, it is 0. Cool. Okay. Any question? All right, let me move on to the OR gate now. OR gate, in the OR gate, okay, we define it like this, okay, Z is equal to X ORed with Y, okay? And symbolically, okay, we have a curved arc here, okay? And then a pointy head here, okay? All right? So we have this is input X and this is input Y, and Z, which is the output here, okay, is equal to X or Y. This is the symbolic form of the OR, okay, and this is algebraic form of the OR. Now, what is the difference between this and the AND? Who can tell me what is the difference between the symbol for the AND and the symbol for the OR?
And is a half circle.
Come again?
And is a half circle.
Excellent, excellent. And the left portion, which is the input side of the AND, is a straight line. This is a curved arc here. Okay. So in order to define the OR, we just compute the truth table or list the truth table of the OR. Okay. So this is, again, this is X and this is Y. Okay. So the Y goes 0, 1, 0, 1. And then the X double the zeros and double the ones, 0, 0, 1, 1. Okay. All right. Now for the OR, it is going to be equal to 1 if and only if X is 1 or Y is 1. Okay. Otherwise, it is 0. So it is 0 here because both X is 0 and Y is 0. Okay. And it is 1 here because Y is 1. It is 1 here because X is 1. And it is 1 here because Y is 1 or X is 1. Okay. All right. So mathematically, say, well, X ORed with Y. We don't say plus, we say OR. Okay. We say OR Y. Okay. Is equal to 1 if and only if X is 1 or Y is 1. Okay. And it is 0 otherwise. All right, so the third gate is the NOT gate, okay, which is defined using Boolean algebra. Z is equal to X complement, where X is the input here, okay? So the symbol for that is this. So you have a triangle here, okay? It's just a triangle with a bubble in front of it. The bubble is extremely important, okay? The triangle and the bubble is extremely important. If you draw it without the bubble, then it is a different symbol. Okay. So the definition is simpler than the two other gates because you have only two possibilities here. One input, two possibilities. The input can go 0 or 1. Okay. If it is 0, then the output is 1. If it is 1, the output is 0. And this is the mathematical definition here. Okay. Now there are other gates as well. But these are the main gates, the and, or, and not are the main gates. However, there are other gates which we will explain in more details later. But for now, I just want you to know them and know their names and their function. Okay. So the first gate that exists other than the and the or and the not is the NAND gate. And the NAND gate is nothing but an and followed by not. Okay. So basically you draw an and then you put a bubble in front of it to indicate an and. Okay. So the truth table for this is you generate the truth table for the and, which is X ANDed with Y, and then you complement these. So whenever you have a 0, it turns to a 1, and whenever you have a 1, it turns to a 0. So in the output, which is Z, okay, here Z, okay, is algebraically equal X ANDed with Y, and then between brackets, okay, we have a prime here to indicate the complement. Okay. Similarly, we can define the NOR gate, which is OR followed by NOT. Okay. And this is the truth table. Okay. And we can also define the XOR gate. Okay. XOR gate, which is something, it is also a composite gate, but it has a different functionality. It's not something followed by something. Okay. So the XOR gate is defined like this. So X XORed with Y, okay, is 1 if and only if, actually, if and only if, okay, X does not equal Y. Okay, so it is 1 in case of X is 1 and Y is 0, or X is 0 and Y is 1. Okay, and it is 0 otherwise. If they are equal, it is 0. All right, and this is the symbol for the XOR gate. This is the symbol. So it is similar to the OR gate, okay, but we double the arc here. The arc at the input, we double it. We have double arc to indicate that this is an XOR gate, okay? I forgot to give you the symbol for the NOR, okay, which is nothing but an OR followed by a bubble, okay? All right. The XNOR, on the other hand, which is an XOR followed by an inverter, okay? So if you invert that, okay, you get what we call a gate that detects equality in this case, okay? So it is 1 when X is equal to Y and 0 otherwise. This is if and only if, okay? So for this reason, we call the XNOR gate the equivalence gate. And the algebraic symbol for the XOR is this symbol here. A plus surrounded by an O, and it's called an O plus, okay? For the XNOR, okay, we don't have a symbol for that. It's just XOR, and then you complement the XOR, okay? Because it's nothing but an XOR followed by NAND. In some books, they denote it by an O dot, okay? A dot surrounded by an O, okay? But we don't use that here, okay? We just use the O plus, and then to indicate the XNOR, we complement that, okay? Any question so far? All right, let's move on. So here is an example. So we would like to sketch the logic circuit of this Boolean function here. This Boolean function f is equal to a ANDed with b complement ORed with b, okay? Now we would like to sketch this logic circuit, okay? So how do we proceed? First of all, applying the precedence, okay, from the precedence rules, we know that the OR is going to be computed last. So whatever the result of this is going to be ORed with B, right? And this is going to be F. So we know that there is an OR at the end here, okay? Additional part here, okay? An OR at the end which takes B, okay, from one side, and from another side it takes what? It takes A ANDed with B complement, okay? So this is coming from the output of an AND gate, okay? AND gate, I just ruined it. Right. All right. So what does the AND gate takes? It takes what? A, okay, and then
B.
B with an OS.
Yeah, so it's B complement, right? So B complement is coming from, there is a B that is having a complemented here, okay? And also we take a branch here of the B and take it to the OR gate. The output of this OR gate is what?
F.
F.
Yeah. Okay. Now the second question is to derive the truth table of F. Now the question is, how many inputs does this function have?
2.
2 inputs, which are
A and B.
A and B. So we list the inputs first. How many possibilities do we have for the truth table?
4.
4. Excellent. Why? Because we have 2 inputs. 2 to the 2 is 4. Okay. And to list them, we say, well, this is going to be a 0, 1, 0, 1, and then followed by 0, 0, 1, 1. Okay. So these are the input combinations. Okay, let me draw some separators so that things become clear. Okay. So what's next? Next, we need to, so for this OR gate, for this F here, to get to be computed, we need this signal here and this signal, right? We need to OR them together in order to get the result. So what is this signal? Is B, which is given here, right? This signal here is B, which is this input here, it's given. But this signal here is not given, so we have to compute it. So this is A ANDed with B complement, right? Yeah, this is the result of the signal. However, before computing this signal here, which is this wire, okay, we need to compute B complement, right? So where is B complement? It's here, B complement. So we have to list B complement first, okay? So B complement is going to be what? Equal to?
Opposite of B.
Excellent, which is 1 0 1 0, right? And then we can compute this now, which is A ANDed with B complement. Because why? Because we have the A and we have the B complement. So we AND them together. 0 ANDed with 1 is 0.
0.
Okay? 0 ANDed with 0 is 0. 1 ANDed with 1 is 1, right?
1.
Excellent. 1 ANDed with 0.
0.
Excellent. Okay? Now all we have to do is to OR this signal with this signal, right? But this signal, we have it already. And this signal, we have it here. So this signal is B, and this signal is AB complement. And if we OR these together, we get F, right?
Yeah.
So 0 ORed with 0 is 0. 1 ORed with 0 is
1.
1.
excellent. And 0 ORed with 1 is
1.
and 1 ORed with 0 is
1.
1.
1. Excellent. What can we say about F? Let me give you a hint. What is A ORed with B? We just want to calculate this by itself. A ORed with B.
0, 1, 1.
0 1 1 1, right? Hold on. For every combination, for every input combination, F, okay, has the same value of A or B, which means they are equal, right?
Yes.
So I can say, well, F, which used to be A, B complement ORed with B, is now, I concluded that it is equal to A ORed with B. So the you can have more than one form of a Boolean function algebraically. However, if you if they are equivalent, then they will have the same truth table. Okay, so the truth table is unique. However, the Boolean functions can be different. And in fact, we just proved that this form here can be reduced. We can get rid of this B complement and get this form here. So it can be simplified. We say it can be simplified by dropping the B complement. This is called the simplification rule. We'll study it later. Okay. All right. Moving on. So this is another example in which we would like now, given the logic circuit, we would like to derive the Boolean expression of it. Okay. So now we just label every signal in the circuit and then perform the operations. That's it. So this signal here, starting with this signal, what does it equal to?
A and B.
A ANDed with B. Excellent. Okay. What about this signal here?
B complement.
Excellent. And this signal, finally.
B
B complement
order C.
or C.
Excellent. Ordered C. So remember that F is nothing but this ANDed with this, right? But because of the precedence, okay, we have to surround this by a bracket because it's calculated together. Okay, it's calculated together here. Okay, so it equals to AB ANDed with B complement or C. Now we would like to also derive the truth table of this function. So how do we do that? How many variables, how many inputs do we have?
2.
3 inputs.
3.
3 inputs. Excellent. They are A, B, and C, right?
Yes.
Yeah. So how many combinations?
8.
8 combinations, which is 2 to the 3. Excellent. Okay, so let me just draw some separators. Can do it quickly. 1, 2, 3, 4, 5. So again, for the least significant variable, we say 0, 1, 0, 1, 0, 1, 0, 1. Okay, and then we double the number of zeros and ones here in the B, 0, 0, 1, 1, 0, 0, 1, 1, and then double for the A, 0, 0, 0, 0, and then 1, 1, 1, 1. Okay, now what do we need to calculate? We need to calculate A ANDed with B, A, B. Okay, so what is this? It's going to be 0, 0, 0, 0, because the A is 0 in all these cases, and then the B is 0 here, and the B is 0 here. It's 1, 1 here. Okay. Next, we need to calculate B complement. Let me put it here. B complement. Okay, which is going to be 1, 1, 0, 0, 1, 1, 0, 0. Okay. And then we calculate B complement ORed with C. Okay, which is this ORed with this. Okay. Now this is equal to 1. Help me do it. Okay. 1 is 0. Tell me if I'm wrong. Okay. 1, 1, 1, then 0, and then 1. Did I get it right?
Yes.
And then finally, my F is going to be the ANDing of these two columns, right? So this is going to be, because of these zeros here, okay, all of this will be 0. Okay, and then this is 0 because of this 0 here. And then this is the only one here. Okay, so what did we learn here? That F is actually equal to, which is A
And B.
B, and it would be complement or C, okay, is equal to, in fact, A, B, C, which is the ANDing of the 3 inputs, okay, because it is 1 only when all of them are 1. Okay, this is what it means. Okay, so again, Boolean functions can be written in many different ways, and some of them are simpler than others. Okay, right, I'm going to stop here and probably stop recording.